Namaste. I am Tipesomi MS, Assistant Professor of Physics, Government Factory College, Haryana. In this video, I am going to present on the properties of stars, which is the sub-concept of astrophysics. Dear students, I hope you all are safe from the COVID-19 by staying in home. Dear students, as you see this picture, this is I have shown in the last video lecture. This is released by NASA. See, this is the special day for NASA, April 24th, 1900. It was the day NASA launched Hubble Space Telescope. Later this, a significant changes in the exploration of the universe, observation and discoveries of many properties of stars. See, this picture, there are the stars having the different color. Some stars have in blue in color, see this is one, and higher mass. Some stars have red in color, a tiny star. Some colors have in, this is one yellow, see this is one red, these are in red, these are in red. Why the stars are in change in the color? Today I am going to talk on what decides the colors, what decides the mass, what decides the temperature. In this slide, I have mentioned some important properties of stars. Those are brightness, color, surface temperature, size or radius of stars, mass, chemical composition, density, etc. Initially, I am going to consider the property of the star, which is the surface temperature. Let me know how the astronomers are going to estimate the effective surface temperature of the star. As we know that when a body is at higher temperature with the surroundings, emits energy. Energy radiated per unit area per second is called as a emittance. Therefore, total energy distribution emitted by the any hot object, which is always function of wavelength. In this case, we are going to estimate the effective surface temperature of the star by studying intensity distribution as a function of wavelength. Therefore, we are going to consider a float or a intensity distribution. Along the x-axis, we are going to consider the wavelength in terms of nanometer. In this direction, the wavelength which is going to increases. In this direction, the intensity going to increases. First, we consider the object is at a temperature which is 1250 Kelvin, which is emits energy which is having the many wavelengths. This is 200 nanometer, 1500 nanometer, 1000 nanometer. In this case, only particular wavelength we got maximum intensity. That particular wavelength we call as a lambda maximum. In this particular wavelength we got from that object, we got maximum intensity. As the temperature of the same body which is increases around 1715 Kelvin, the intensity peak which is going to increases. In addition to that, the peak which is going to shifting towards the longer wavelength. That means displacement takes place. The lambda peak which is going to displacement takes place. For temperature which is 2000 Kelvin, the most intense radiation which is here. Therefore, by this studying this, we are going to conclude that increase in the intensity of the radiation with the increase in the temperature. And also in addition to this, that lambda peak which is going to shifting towards the smaller wavelength as the temperature increases. Therefore, we are going to conclude that intensity varies with the wavelength and it is maximum for a particular wavelength, that is we call as lambda maximum. That lambda maximum which is decides the color of the star. Therefore, for measuring the effective surface temperature of the any star which is going to use this equation, this is we call as Wien's displacement law. The statement of the Wien's displacement law which is the most intense radiation emitted by the star which is inversely proportional to the temperature, as well as the temperature increases, the lambda maximum which is shifting towards the longer wavelength, smaller wavelength. For sun which is emits a broad spectrum of X-rays of wavelength 2 nanometer to radius of wavelength 10 nanometer, but most intense radiation reaching the earth's surface which is visible light of wavelength 500 nanometer. By keeping these values, we are going to estimate the effective surface temperature of the sun which is gives 5800, that means 5800 Kelvin. Therefore, hence sun appears as yellow in color. From the last slide, what we learn, the most intense radiation we got from the particular hot body of particular wavelength, that particular wavelength which is decides the color. Let me know this picture, this is the lambda peak. This is the most intense radiation reaching the earth's surface by this color. This is about 1000 nanometer. When you keep this 1000 nanometer in that last equation, we have got 3000 Kelvin surface temperature of this size. Therefore, this is red in color. Again, this we consider, this is another one yellow color star. What is the most intense radiation reaching the earth's surface which is around the visible light. Therefore, this the temperature which is of this star is 5800 Kelvin. Another star we consider, this is the maximum peak which is appears in the region of ultraviolet radiation. That's why ultraviolet radiation which is a wavelength, when it keeps in the last equation, we have got 10,000 Kelvin. These are the in blue color star. Blue color star is compared to this color 3000 Kelvin, 5800 Kelvin, 10,000 Kelvin. The red color star, the temperature is low in color. Blue color star, temperature is high in color. Therefore, we consider where these are in cool star, these are in hot star. Therefore, hottest stars are in blue color, coolest stars in red in color. The medium which is orange or yellow. Therefore, the star's color shows the temperature of its surface. By the color, we are going to decide what is the temperature. Therefore, because of red, the red colors having a surface temperature is 3000 Kelvin. The blue color, this is the color stars appears as a blue color. Therefore, these colors, these stars having a surface temperature is almost more than 10,000 Kelvin, 9,000 Kelvin, 11,000 Kelvin. Therefore, the surface temperature of the star varies from 3000 Kelvin for red stars, that is Betelgeuse. Betelgeuse, one of the best red giant star, and to the 15,000 Kelvin, which is the blue star, which is a regal, and other color stars having the temperature between these two, red and blue color. Then finally we are going to conclude that star's color depends on its surface temperature. In the beginning what we said, what color which are going to, what the surface temperature of the star which are going to decide by on its color. Cooler stars tend to redder in color, while hotter stars having blue appearance. Let comes to the another important property, which is luminosity. Luminosity of the any star we are going to measure by the absolute brightness. Absolute brightness of an object is measured by the total amount of energy radiated per unit area per second is called as a luminosity. By the Stephens-Boltzmann law, as we know, this is one luminosity or total energy emitted by the object per unit area per second we call as luminosity. L is equal to A sigma, this is the Stephens constant, this is the Stephens constant, this is absolute temperature, where in the case T stands with surface temperature, that means effective surface temperature, and A stands with surface area, and sigma is the Stephens constant. So here, according to this equation, we are going to conclude that luminosity of the any star, which is mainly depends on surface temperature and also surface area. If the surface area is higher, luminosity is also high. Students, remember this point. If surface temperature is higher, luminosity is also high. In addition to this, surface area if is higher, luminosity is also high. The surface area we are going to measure the 4 pi r square, which is considered as a sphere. This is luminosity of the any star. So here let me going to find the luminosity of the sun by keeping the equation, the radius of the sun, which is 6.96 into 10 raised to 5 kilometer. As we said, surface temperature of our sun is around 5800 Kelvin. Sigma constant, which is equal to 5.67 10 raised to minus 8 watt per meter square, Kelvin to the minus Kelvin to the fourth. Here, what is this sign? Denotes the sun symbol. We get luminosity of the sun, which is equal to this much, 3.845 into 10 raised to 26 joule meter square per second. This is the luminosity. After these values keeping in this equation, this is the luminosity of our sun. That means total amount of energy radiated per unit area per second by the sun in all direction, that is the luminosity. But also in addition to this, size of the star and its surface temperature determines its luminosity. Yes, size of the star, that means R, size of the star and surface temperature, which is determines the luminosity. Therefore, luminosity L, which is equal to 4 pi d sun and B sun. Here this is one, here indicates this is solar total energy reaching the earth's surface per unit area per second from the sun in 1 second, that is solar constant. This is what we call d, which is a distance of the sun from the earth. For luminosity for any star, which is going to equation. By knowing the luminosity of the sun, distance of the sun from the earth, and also solar constant of the sun, by knowing this equation, we are going to estimate the luminosity of the any star by the equations. L is equal to, this is relative distance of the star, this is solar constant. Simply, students, we remember luminosity of the any star, which is mainly depends on the surface temperature and surface area, that means size of the star. The next property of the star, which is size or radius. As we know that surface temperature of the star is going to estimate by the rate of production of energy at the core, and also surface temperature, also color index. Therefore, the size of the star we are going to estimate from its luminosity and surface temperature. As we know that energy radiated per unit area per unit time of any hot object or any black body, which is equal to E is equal to sigma T raised to 4, where E is the energy radiated per unit area per second, where sigma is the Stephen's constant and T is the absolute temperature, that means 4th power of the absolute temperature. In addition to this, absolute luminosity L is equal to 4 pi r square E, where r is the radius of the any star. That means our aim is to find out that is r. From the equation on 1 and 2, we are going to get L is equal to 4 pi r square sigma T raised to 4. Therefore, by after simplification, r, the radius of the star, that means size of the star, r is equal to L by 4 pi sigma T raised to 4 under the square root, where L is the absolute luminosity and T is the temperature. By this equation, we are going to conclude that radius of the star or size of the star, which is directly proportional to the luminosity. Luminosity is high, radius is also high. Remember these points, very important to learn the next concept, students. If the temperature is high, radius is low. That is also another, that means under the square root. So, by keeping the solar constant, that means the sun's luminosity, by keeping this is the absolute luminosity of the sun and surface temperature of the sun, and this is the value of Stephen constant. By keeping these values in this equation, and we get the radius of or size of the star is 6.96 into 10 raised to plus 5 kilometer. This is the size of our sun. We are able to measure the size of the any star by using the L and R. This is the solar unit. That is equal to, this is the we are able to find out the size of the any unknown star by knowing the radius of the sun, absolute surface temperature of the sun, luminosity of the sun. As by this equation, some of the stars in the universe having their size is 2 kilometer or few kilometer. Largest size of the stars in billion kilometer also present in this one stars. Let me come to the another important property of the star, which is chemical composition. Mainly chemical composition can be determined by the emission or absorption lines in the spectrum. Yes, normally the star consists mostly hydrogen and helium. That is mostly when we comes to in terms of percentage, hydrogen is 91%, helium is 9%, and with 0.2% is heavy elements. That is in terms of mass, when we say this is hydrogen atom is 74.3%, helium is 23.4%, and only around 2% remaining elements. Those are oxygen, carbon, nitrogen, iron, nickel, chromium, and etc. And some of the another other heavy elements which is sulfur, magnesium, chromium, aluminum also present. All these present in the neutral atoms exist on the surface of the star like the sun. That is so, as the temperature is so hot, so high at the core, the only bare nuclei which are present. This is one. Let me comes to the another important that is the mass of the star. This is the main important property of the star. How the mass of the objects can be found. That's very important. There are the many methods, indirect methods we are going to measure the masses of the stars. Firstly, the mass of an object is obtained from its attraction on the another bodies by the Newton's Coulomb law of attraction or universal law of attraction, universal law of gravitation, that is F is equal to G m1 m2 divided by r square, that is in terms of Newton. By this, we are mass of the sun estimating by studying the motion of the planet around it, that is mass of the sun is around 1.99 10 raised to 30 kg. This is one of the method to find out the masses of the star. One is of Newton's law of gravitation. What is the velocity of the planets revolving around the sun is another method. And also another method, there are the many stars, mostly 99% of the star in the universe, there are in the present as a binary stars. These binary stars revolving around the center of mass, and it reveals the mass of the binary stars. Very important. Therefore, to measure the masses of the binary stars, that is, we use the equation that is Kepler's third law. Square of the period of the planet around that binary center of mass, which is equal to the cube of the semi-major axis. That is ratio of these two, which is equal to constant. That constant we call as a total mass of the binary system. That means m1 plus m2, these two are the masses of the two stars, which is equal to the mainly measured, that means period of that is orbit and cube of semi-major axis, where a is the mean distance between the star and period of the orbit. This is one method. Another method is also mass of the star A, mass of the star B. Ratio of these two equal to the distance from the center of mass B, distance from the center of mass A, and velocity of the star B and velocity of. This is also another method to find out the stars. Yes, let me come to a finally end. This is one. By knowing these properties of the stars, what is initially we consider the surface temperature, luminosity, size, chemical composition, mass. We are trying to answer these following worksheet questions. Thank you very much, students. Stay home, be safe. Thank you.